Welcome to the Flip lecture on escape velocity. Now, this usually comes up when we talk about the forces required to allow the launch of a rocket into space. What sort of velocity is needed to overcome the pull of gravity? And so that's what escape velocity is. It's the velocity required for an object to escape the gravitational attraction of the central body, in this case Earth. So let's see if we can understand that and derive an equation. And to do that, I'm going to draw Newton's cradle. You've probably come across these before with kids. Okay, you have steel balls and you lift one steel ball up, you drop it and it comes along and the last steel ball comes out the end. You pick two steel balls up, you drop them and two steel balls come out the end. Hours of fun, but it's really looking at the law of conservation of energy. So two balls go in, two balls go out. And what that is it's looking at, if you pull that back, you're giving it some gravitational potential energy, right, which is designated by UP. So we've got some gravitational potential energy, but then when you let it go, that gets converted to kinetic energy. And therefore we know that's the initial, and of course we have the final momentum as well. So the mechanical energy of the system is conserved. What you get before is what you get afterwards, ignoring the small, minute losses due to sound and to heat as a result of friction between the balls, right? So if we think about this, we can say that the kinetic energy initial plus the gravitational potential energy initial is equal to the final kinetic energy plus the final gravitational potential energy. Now, if you remember back to how you defined gravitational potential energy is zero at infinity. Okay, so if we remember, if we have a body here, let's say that's Earth, and we have an object, it can be a box, it can be you, it can be anything. As you move that box further and further away from that central body, you have, of course, the pull of gravity acting in that instance there, over that distance, and that creates an energy value, gravitational potential energy. Very close to the surface, we use the value of the height times the mass times the acceleration due to gravity, g. But of course, as we get further and further out, we start using another equation, and the gravitational potential energy is minus g m1 m2 over r, where m is the mass of body number 1, so we could call it the Earth. Alright, so we can go me, and then we can go m2 as the mass of anything else. So if this is a rocket, let's call it mr. And so as the radius increases, the object's getting further and further away, and its gravitational potential energy is getting bigger and bigger and bigger. But then, of course, we get to a position here at infinity. At infinity, by definition, it's so far away that it has zero gravitational potential energy, because I guess the pull of gravity between the two is so weak, it's not going to come back. So at infinity, GPE equals 0. That means that everything between that point, infinity, and your starting point is now less than 0, and hence that's why we've got a negative sign. So that's the equation that we use, and I hope you probably can't see that because I've written it so high. Oh well, I'll write it again down here, right? So we have gravitational potential energy being that equation there, so we go plus, and we're going to write that in, g, the mass of the Earth and the mass of the rocket, over r. The kinetic energy for a moving body is a half m r v. Now that's the escape velocity of the rocket squared, right? And so all of this is initial, and we said at infinity gravitational potential energy is 0, and of course at infinity the kinetic energy is 0. So really, this whole equation equals 0. So if we do this equation out, we've got a half the mass of the rocket escape velocity, right, minus g, mass of the Earth, and times mass of the rocket over r equals 0. We move this onto the right hand side, so we've got a half mass of the rocket, escape velocity, equal to gravitational constant, mass of the Earth, mass of the rocket over r. And so now what we can do is we can go, okay, well, let's get rid of the mass of the rocket because that cancels on both sides. Right? A little bit of algebra there, but if we divide this side by mass of the r, we divide that side, which is the same as timesing by the reciprocal, and so they cancel. So we then have up here, I'll write this up here, then we have a half velocity e squared, right? The escape velocity is gm of the Earth over r. So we want to get rid of this, so this is basically saying velocity, escape velocity over 2 is gme over r. So what we've got to do is times by 2 here and times by 2 over there, so the escape velocity is equal to 2gme over r, and then we take the square root. Okay, and so what we can see is the escape velocity of an object is dependent upon the gravitational constant there, g. It's dependent upon the mass of the central body that you're on, and of course the distance or the radius away. Okay, and so you would expect therefore that as the mass gets bigger, then so should the escape velocity. Okay, and it also depends on r as well. Okay, so look at the escape velocity calculations for a variety of different masses and planets. I'll make another video on looking at that, comparing 3 different planets and their escape velocities, and you'll be able to see the relationship between mass, radius, and escape velocity. Okay, that's it for that one. Hope that makes sense. You don't have to derive it every single time, just memorize that. But it's always good if you can understand the fundamental principles of how we got to that equation in the first place. Okay, see you in the next video.